Here are two practice multiple choice problems that focus on the concept of power. First one. An object of mass m is lifted at constant velocity, always an important phrase to note, a vertical distance h in time t. The power supplied by the lifting force is what? This is basically our classic scenario from which the unit of horsepower is derived. We've got a mass that is lifted a certain distance in a certain time, lifted at a constant velocity. We want to know the power input required to make this happen. Since it was lifted at a constant velocity, we know that the net force on it is zero, so the applied force must be equal to the weight of the box. And we'll be using that along with this definition for the work that was done. Since our force is constant, given that our velocity is constant, we can compute the work from this expression. What we want is the power, so I'm going to compute it two different ways. First, the average power input required is given by the total work that's done divided by the total amount of time that elapses. So the work that was done is given by fx delta x plus fy delta y plus fz delta z, but we know that there's no movement going on in the z direction. In fact, we know there's no movement going on in the x direction either. It's just being lifted straight up. So just fy delta y divided by the amount of time that elapses. Okay, the force that's required to lift it, I argue that force must be equal to the weight of the block, since again it's lifted at constant velocity. So that would be mg is the force required. The height that it went, the delta y, is a distance h. The time it took was time t. So there's our answer, mgh over t. Or I could solve it one other way. I could note that the power input required is also equal to the force applied dotted with the velocity vector of our object. And the force and the velocity dot product can be expressed using this representation of the dot product, magnitude of this vector times magnitude of that vector times cosine of the angle between them. Our applied force is up and the velocity vector is up, so the angle between them is 0. So cosine of 0 is just 1. So we have the instantaneous force times the instantaneous velocity. But again, our force is constant, so the instantaneous force is the value the whole time, which I've already argued is mg. And as for the instantaneous velocity, well, we're told that's constant, and so our velocity can be found, our Vy can be found, since it's constant, it would be the same expression as for an average velocity, just delta y over delta t, the distance traveled in the time that it takes. So that would be a distance, a height h over time capital T. So h over t, there's your velocity. And so again, we have mgh over t. And we've confirmed the power output using these two definitions for power, these two ways of expressing power input. But we could actually have arrived at this answer from among our 5 options here without doing any work, using a method that I highly, highly, highly recommend for multiple choice problems. Look at the units of your answer options. Look at the dimensions of your answer options. For instance, A, we have a mass times little g times the distance times the time. Well, mg we know is a force. So mg is newtons. Multiply that by a height in meters times a time in seconds. And this quantity has units of newtons times meters times seconds. That is not a power. We're looking for a power. Newton meters would be joules, so energy, times seconds, but that's not power. Next one, mgh over t. That's the answer we did arrive at. Let's check it. mg is in newtons times h, a height, in meters, divided by t in seconds. There we go. Newton meters per second. Joules per second. That is a power. Next one. mg, that's in newtons divided by height times time. So newtons per meter per second. This just doesn't have the right dimensions. It's not a power at all. Likewise here, mg, that's newtons times time, seconds per meter. Newton seconds per meter, that's not a power. So we can rule out options D, B, whoops, B's the good one. We can rule out D, C, and A on dimensions alone. Even without doing any physics here, knowing that we're looking for a power, A, C, and D are not powers. So our answer is either B or 0, and you just have to think about the physics to distinguish between options B and 0. So I suggest this method of eliminating answer options on multiple choice questions. Look at the dimensions of the answer. It's very, very useful. Okay, one more example problem for us to do here. Oh, wait. I know. Now that we've got this answer here, the mgh over t, I wanted to use that to revisit our horse lifting the box here once more and note where this definition of the horsepower comes from. So 1 horsepower is defined as the power required to lift 75 kilograms at a height of 1 meter in 1 second. So mgh over t, our mass, 75 kilograms times g, 9.8. Mg times h, so a height of 1 meter, so times 1, divided by 1 second. 735 watts would be the power required. Hence the equivalence, 1 horsepower is about 735 watts. Okay, and there's a difference between a metric horsepower and just a horsepower 746 versus 735. That's just a historical quirk there, that these are close to but not quite the same as each other. But anyway, that's basically where the unit conversion comes from. Okay, now this second multiple choice practice problem. A person pushes a box across a horizontal surface at a constant speed, note constant speed, very important, of 0.5 meters per second. The box has a mass of 40 kilograms, and the coefficient of sliding friction, meaning the coefficient of kinetic friction, mu k, is 0.25. Power supplied to the box by the person pushing it. Okay, here's my free body diagram. We know our forces, the applied force and the force of friction, are balanced because constant speed. Okay, here I think the most straightforward way to compute the compute the power input to the box by the person would be to dot the applied force with the velocity of the box. So that'll be magnitude of the applied force times the speed times the cosine of the angle between them. Well, if we're just moving horizontally in the direction of the push, then the angle between them is 0. Cosine 0 is 1. So now we would just note that our applied force must be equal to our force of friction. So we would express on the page our expression for the force of friction, mu k times the normal force. This is what we would write out if it were a free response problem and we were showing our steps, showing our thought process. Normal force is equal to our force of gravity, so mu k mg. That's our force of friction, must be equal to our applied force. So mu k mg, that's our force. And our speed is given here, times our speed v. So 0.25 times the mass of 40 kilograms times little g times our speed of 0.5 meters per second comes out to about 49 Newton meters per second, or 49 watts. Put my little serifs on the W to indicate watts as opposed to work. So it's about 50 right there.